Hi everyone. So I'm Masahiko Arakawa, Kobe University. Kobe is near here. I hope you enjoy this area in Japan. So it's my honor to have a presentation in this conference. I will talk as a representative of these 6 authors. So our chapter title is Exploration-Based Reconstruction of Planetesimals. So here is the contents of our chapter. I'm responsible for this chapter, this section, but I will talk all of them today. So I'd like to talk about a small asteroid based on the planetary exploration and their relationship to the planetesimals. And I'd like to suggest that the small asteroid, a second or later generation planetesimals suffering the catastrophic disruption and reaccumulation. But the constituent materials mostly keep the original information of the first generation planetesimals. So we can obtain a lot of information of the first generation planetesimals by using return samples from these small planets, small bodies. So first of all, I'd like to summarize the problems in the planetesimals formation and evolution as follows. The first problem is that there are many obstacles in the process of dust growing into planetesimals in the solar disk. There are the bouncing, fragmentation, and radial drift barrier in the dust growth. The radial drift barrier can be cleared if the dusts are fully fractal aggregates, but the astronomical observation show that dusts are compact spread aggregates. And more, a moderate level of turbulence would suppress the dust setting over gravitational instabilities to form planetesimals. The second problem is that we don't understand how much of the radial mixing of the planetesimals and their fragment during the planetary accretion stage. So, what was the effect of the possible migration of giant gas planets? And how did the radial mixing influence the origin of water and the organics on the early Earth? So the clues to solve these problems may be found in small asteroid and comet. So asteroid and comets may be a good analog of planetesimals. As you know, there is a depth barrier of planetary growth between centimeter-sized pebbles and 100-kilometer-sized planetesimals. And the physical property and dynamical behavior of these intermediate bodies in the depth valley are still unknown. The recent exploration, including return samples from small asteroid and comet, shed light on the study of these objects in the depth valley. For example, the parent bodies of a small asteroid should be fossil of planetesimals, and many of them are byproducts of collisional fragments events. And there are small self-gravitating unconsolidated bodies like planetesimals. So the Ryugu sample suggests a radial transport of planetesimals from beyond the Saturn orbit to in the asteroid belt due to giant planet migration in the plot solar disk. So we explain after. So our chapter is exploration-based reconstruction of planetesimals. So using these results from different missions, we review what much kilometer to and sub-kilometer bodies tell us about the planetesimals from the perspective of shape, structure, impacts, mass ejection, and other processes. Furthermore, we also explore how these new results fit in with current scenarios of collision evolution and growth or disruption for planetesimals. So next, I'd like to talk about the rendezvous exploration of small asteroid and comets. So here, I'd like to focus on the topics of asteroid, Ryugu, and Bennu. So they are the intermediate weight member of small bodies. So there is a photo show the asteroid Itokawa and Ryugu and Bennu. So this is not asteroid, it's a comet, nuclei Chernomukh-Gerasimenko. So this is asteroid Ryugu, so explored by Hayabusa 2 mission, Japanese mission. Hayabusa 2 investigated on-site this asteroid from 2018 to 2019 for 1.5 years. This is a small sheet-type asteroid with a diameter of about 900 meters, and it has a top shape. So it is very obvious that Ryugu has a clear bulge on the equator, and the surface is covered with large boulders like this. The bulk density is about 1.2 grams per cubic centimeter, a little bit heavier than water, and the estimated bulk porosity is 50 to 60%. So that means half of the body is space. So Ryugu is considered to be loosely reaccumulated lava pile body. According to the intensive study of Ryugu by Hayabusa 2 mission, we have now a standard model for evolution of Ryugu from parent body to the current state. The parent body of Ryugu was formed 4.5 billion years ago, and it could have an extremely uniform interior. So 1 billion years ago, parent body may be disrupted by S-type asteroid collision. Then the top shape was formed less than 20 million years ago, and after that, orbital evolution occurred at 8 million years ago, and it could be excursion toward the sun. Then the rotation slowed down the spinning. So as you can see that the Ryugu is not the first generation planetesimals. The parent body was disrupted more than once, and the fragments were reaccumulated by self-gravity to form lava pile body. So Ryugu is a second or later generation planetesimals, we think. So asteroid Bennu is also a small lava pile asteroid explored by NASA's OSIRIS-REx mission. So there are several similarities between Ryugu and Bennu. So they are top-shaped lava pile bodies with low density about 1.2 gram cubic centimeter. They have no fine regulars, the low albedo and flat optical spectra. So the borders have low thermal inertia, suggesting the low mechanical strength of several hundred kilopascal. And furthermore, the surface have extremely low intergrain cohesion. It's less than 1 Pascal, almost no cohesion. But some difference in the composition of water-bearing material, water-bearing mineral was observed. The reason of this difference will be solved after OSIRIS-REx returned the sample this year, September. So next, I'd like to talk about the returned sample from Ryugu. So these videos show the touchdown operation of Hayabusa 2 to recover the sample. Hayabusa 2 gradually descended toward the surface, and the surface material was sampled by impactor at the moment of the touchdown. Then Hayabusa ascended by jetting gas thruster. So we can find dust cloud and many fragments ejected from the surface by this gas thruster. The dust cloud may indicate that the surface is easy to move and has weak cohesion. So the collected surface samples returned to the Earth on December 6, 2020. So this movie shows the trajectory of the re-entry capsule. And this photograph shows one of the returned sample with a size of 1 centimeter, so large one. A sample analysis showed us that there are a lot of hydrated minerals in it. And it means that Ryugu's parent body had liquid water, we confirmed. So By further analysis, it is shown that the Ryugu's sample was almost similar to the most primitive cone-like Ci. And liquid water was discovered in the fluid inclusion, like this. Here, hole shows the liquid inclusions. Actually, fluid in inclusion was CO2-rich brine. This means that the apparent body of Ryugu could be formed at a region colder than CO2 snowline, so which is CO2 condensation temperature. Here is evidence of CO2. So we have now results showing the isotopic anomalies of heavy metals and oxygen. So this figure shows the plots of isotope content for titanium, chrome, oxygen, and iron. The data can be clearly separated into 3 groups in this figure. So non-carbonaceous cone-like, carbonaceous cone-like, and Ci cone-like, and Ryugu. So Ryugu and other Ci cone-like may have been much further than other carbonaceous cone-like, such as Cm, Cv, and Co here. So these different type of parent bodies could be scattered and migrated in the solar nebula, we think. So next, I'd like to talk about the connections between shapes and processes. So Labrapai asteroids show unique shapes, so we can infer their unique evolution processes. So this unique shape may be categorized into 4 different shapes. The first one is round shape here. This shape includes top-shaped bodies like Bennu and Ryugu. And the second shape is an elongated shape. Geomorphos is an example of this shape. The third one is a contact binary here, a shape apparently having 2 components softly touching each other, like Itokawa. Some asteroids have similar shapes. And any asteroids not categorized in them are considered to be unclassified. So each shape has a unique structural condition due to its rotational state. The second and third law here show the most sensitive locations on the surface and the interior when they have a homogeneous structure shown by yellow color. So among these shapes, top-shaped asteroid with a round shape category are one of the most common shapes. So Ryugu and Bennu and Didymos here are example of top-shaped bodies. The next slide focuses on the evolution mechanism of top-shaped asteroids. The top shapes are featured by their unique asymmetric shapes with clear equatorial ridge or bulge. The top-shaped asteroids have a unique evolution process due to rotation after reaccumulation. This slide shows an overview of the evolution process depending on the structure and the rotation state. The schematic illustration A shows how top-shaped asteroids evolve when the spin and the internal structure are provided. If top-shaped asteroids have homogeneous structure, then they continuously become oblate. As the spin becomes faster, eventually collapsing to be shed. So in Fig B, if the structure is homogeneous but supported by high strength, the original shape remains intact. However, when the internal stress reaches yield strength, it collapses catastrophically. Finally, so in Fig C, if an asteroid has a weaker layer on the top of the core, so the surface region is firstly influenced by rotation and removed. If the spin continued to become high, the internal core eventually collapses. So these results show that the rotation speed is important factor to determine the shapes and the fate of small bodies. So, as I previously talked, that the Ryugu is a second later generation planetesimals, and it could be formed by catastrophic disruption and reaccumulation on impact fragments by self-gravity. So the numerical simulation was conducted to study the relationship between the first generation and the second generation planetesimals. So in order to simulate an asteroid disruption, the simulation requires to compute two different physical processes with a quite different timescale. So one is to compute the fragmentation phase, which includes the propagation of a shock wave and the cracks into the target. It is a short timescale process. Another is to compute the gravitational phase between the generated fragments. It's a long timescale process. So in order to model the fragmentation phase, two different numerical techniques has been used. They are 3D smooth particle hydrodynamic impact code, SPH, and the grid codes such as ICEL and CDH. And these models have fracture and porosity, include strength plus fraction, made by the drug pressure-like yield criterion, and porosity shown by the based on the P alpha and epsilon alpha model, and equation states such as tritson, aneos, and sesame. And in order to model the gravitational phase, PKT grav code has been used. So PKT grav is a parallel KT3 gravity code, and it is combines parallelism and tree code to compute forces rapidly. So it computes the gravitational interaction of generated fragments and their potential reaccumulation through their mutual interaction, mutual attraction. Next, I'd like to show the example of numerical simulation for catastrophic disruption and reaccumulation. So this simulation shows the formation of an irregular shaped small body due to reaccumulation. As I was shown in the previous slide, the simulation was conducted separately for fragmentation phase and the reaccumulation phase. The left animation shows the fragmentation phase for 100 km impacted at 5 km per second. So typically, the target is pulverized into solid fragment to 10 to 100 meter in diameter. And the right animation is the reaccumulation phase, and those solid fragments shown by green dots reaccumulate due to their mutual attraction and form lava pile. The final shape, in this case, the accumulated body is like asteroid Itokawa here. And next, I'd like to show the formation of a top-shaped small body due to reaccumulation. So I'd like to remind you the top-shaped asteroid Ryugu and Bennu here. So this animation is the reaccumulation phase for disruption of 100 kilometer sized body. So you can see that the solid fragment reaccumulate and form lava pile during gravitational phase. So this simulation also calculates the impact heating during the collision. The heated temperature was shown by colors from blue cold region to red hot region. So you can see that the most accumulated material is not heated or compacted. It means that the reaccumulated fragment keeps a pristine state of the material. So we can expect that the recovered sample from Ryugu keep the original state in the parent body. So we can summarize when the first generation planetesimals was the size of 100 kilometer, the asteroid smaller than 50 kilometer originate from the disruption of a larger planet body and have lava pile structures. So they are the second generation planetesimals. Next, we apply the same numerical method to the formation of comet nuclei. This photo shows the comet nuclei explored by the space mission. So you can see the shape of the comet nuclei is mostly elongated or bilobate body. So any formation theory for comet nuclei, we have to account for the existence of these bilobate or at least elongated bodies. So as you know, the comet nuclei are supposed to be fossil of icy planetesimals, and it could be the first generation planetesimals. But the size of the nuclei is several kilometers, which is rather smaller than 100 kilometers. Thus, here we discuss the possibility of the second generation planetesimals for the comet nuclei. That is, can catastrophic disruption lead to bilobate comet? So then, these big questions were studied by the numerical simulation. So in this calculation, the 10 to 100 kilometer size icy bodies are impacted at wide velocity range from 20 meter per second to 3 kilometer per second. So this movie shows the result of the collision at the impact velocity of 20 meter per second. Low velocity collision and no cohesion, but angular repose is 18 degrees. And this animation focuses on the second largest remnant at the center. So at the left on the slide, so final lava pile bodies formed in this simulation are shown. So we can find many of elongated bodies as a result of simulation. So in some cases, for the catastrophic disruption, for example, a bilobate body was formed as the impact velocity of, in this case, 150 meters per second. And it is found that the heated and compacted material does not reaccumulate. So this means that reaccumulated lava pile body is almost composed of pristine material. This means that it includes a lot of volatiles in it. So the numerical simulation for the catastrophic impact for icy bodies show that the low speed impact occurred among reaccumulated fragments. So, and the majority of volatile are kept intact during the catastrophic disruption. So most of material can remain pristine. Bilobate and elongated shapes are formed in a catastrophic disruption, as well as bulk densities are consistent. So this means that the formation of 67P Cheremakov-Gerasimenko and bilobate comets can happen at any time from collisional disruption. So next, I'd like to talk about impact cratering and seismic shaking on small lava pile bodies. Here, I'd like to introduce Hayabusa-2 impact experiment on asteroid Ryugu. So it was conducted to recover the subsurface material from Ryugu, but it was a good opportunity to study a cratering process on the small lava body with microgravity. The small carrier impactor with a size of 13 centimeter and mass of 2 kilogram was impacted on the surface of Ryugu at 2 kilometers per second in this experiment. The ejector curtain was observed in situ by deployable camera, and the artificial impact crater, we call it SCI crater, was observed by the onboard camera of Hayabusa-2. So here is a pre and post image of the impact area. Then we can find the artificial impact crater at the center. And the shape model of this artificial crater is shown here. So we can find the elevated rim around the crater. And the crater diameter is about 15 meters, and the depth is about 2 meters. And next, this slide shows the animation of ejector curtain growth observed by DCAM3 camera. So we can determine the crater growth time is about 200 seconds by using these images. And after 200 seconds, ejector deposition occurred. So this time scale is almost consistent with a theoretical time scale of 250 seconds, which is estimated by the crater formation theory in the gravity-dominated region, which means crater size was constrained by the gravity. So we can propose that crater formation on Ryugu with microgravity of 10 to the minus 5g occurred in the gravity-dominated region, not the strength constrained, never constrained the crater size. Next, we discuss the cohesion of Ryugu's surface based on the result of SCA crater and the conventional crater scaling law. So this figure shows the crater radius estimated by the crater size scaling law in the strength-dominated region. So two typical weak material are shown here. So they indicate how crater radius increases with a decrease with the strength. So like this. This line shows a SCI crater radius of 7.3 meter. So when we choose weakly cemented basalt for the analog of Ryugu's surface, the surface strength should be smaller than 1.3 Pascal. So this may show that the upper limit of the surface strength is less than a few Pascal. So actually the crater was formed in the gravity-dominated region. It was clarified by the ejector curtain growth. So the crater radius can be calculated by the conventional scaling law like this by scaling. And the SCI crater size can be reproduced by the parameter of the dry coarse sand like this one. So although the Ryugu's surface is covered with various sized boulders like this one, the impact crater can be reproduced by the parameter of dry coarse sand like this. So we also observe the seismic shaking during the SCI crater formation. So distribution of displacement of boulder after impact shown in the middle image. So this colors the displacement here. We can see that the displacement as small as a few centimeters induced by SCI impact. They can be observed beyond 30 meters far from the crater center. The right figure showed the impact-induced acceleration changing with the distance, and it was obtained by the laboratory experiment, so this line. So that figure shows the area showing the disturbance. So this pink and blue area is much the area where the impact-induced acceleration is above the surface gravity of Ryugu, so this area. In summary, the impact experiment on Ryugu clarified that the surface of small rubber body was easy to move and the cohesion was less than a few Pascal. So next, I'd like to talk about material ejection for small rubber bodies. So there are several mechanisms for the mass ejection from small bodies. So one is a tidal disruption. So rubber asteroid passing close to the Earth at low relative velocity can be spun up and pulled apart by tidal forces. So this is an example of tidal deformation and mass ejection for a few kilometer size rubber body. The outcome of the mass ejection depends on the parameters like periapsis, velocity, spin period, long axis orientation at periapsis, and the spin axis orientation. So next mechanism is a yaw effect. So when an asteroid absorbed and emitted sunlight, so radiation produces a change in the asteroid spin rate and obliquity. So it is called Yob torques. Here is one example of Yob effect on a small low-profile body. It shows the rotation mass shedding by Yob spin up. So left is a top view and right is a side view. The spin up by Yob torques produces downslope movement toward the equator and eventually mass shedding. It can be one of the reasons for the creation of binaries of asteroid. In summary, the small low-profile body is easy to deform and eject mass due to several mechanisms, and sometimes the ejected mass may create a satellite to form a binary. Finally, I'd like to talk about the discussion on the perspective in this chapter. First of all, I will discuss about the constituent of planetesimals. So planetesimals were considered to be composed of pebbles. So these pebbles may be related to the following evidence discovered by explorations. So Ryugu's samples show the apparent frequency peak of particles at 1 millimeter to a few centimeters in diameter. And the low thermal inertia of boulders on Ryugu and Bennu is consistent with these boulders having a polar structure made of constituent particles a few millimeters in diameter. And secondly, I discuss about the size of planetesimals. The expected size of planetesimals is about 100 kilometers when they are formed by the streaming instability. The two lobes of 27P Cheremek-Gerasimenko apply model, but they are too small, a few kilometers, because to have been created by streaming instability. So they may have formed through direct collision of pebbles or collision disruption and reaccumulation. But fluffy fractal aggregates found in 67P Cheremek-Gerasimenko are extremely fragile, so that the presence of such a structure challenges the collision models for relative velocities larger than 1 meter per second. So further studies are required to clarify the formation process of comet nuclei and the typical size of icy planetesimals. And third, I'll discuss about the planetesimal migration in the early solar system. Based on the return sample analysis of isotope and the magnetic field, the apparent body of Ryugu is expected to have been scattered largely. It could move from outside the Saturn orbit to the inner asteroid belt. So finally, I'd like to say perspective. The return sample by Hirabayashi and the samples to be returned by OSIRIS-REx this September are expected to provide a lot of information. So their information related to the origin of carbonaceous asteroid, and possibly on the information and the evolution of icy planetesimals. As you know, the current theory of planet accretion has a number of unresolved issues. So a multidisciplinary effort involving small body exploration, so experiments and numerical simulations remains crucial to reveal the true nature and role of planetesimals. Thank you for your patience. That's it.
Okay, so it's time for question and discussion. Yeah, okay.
All right, thank you for an interesting talk. I'm Ryo Tazaki from University of Grenoble-Alpes in France. So I was wondering if there are any attempts at deriving the refractive indices of Ryugu samples And I'm asking because the refractive indices are very important to try when we try to make connections between solar system materials and dust particles in protoplanetary disks proved by astronomical observations like ALMA.
Yeah, I agree with you. So I have to, but sorry, I can't understand your question.
So is there any attempts at deriving the refractive indices of the Ryugu samples?
So there's a lot of analysis related to the refractory elements of samples, but I'm not so specialist to analyze the samples, so I cannot present in this here. I'm sorry.
Okay, thank you.
Thank you. Vlad Lyra here, New Mexico State. I was wondering about the conclusion that you drew for 6.7p, because the same thing cannot be said about Arakawa, right? That it's that is coming from collisions. That wouldn't be the case. Arakawa in the Kuiper belt, it's two lobes of 20 kilometers each, and it's pristine, right? It's formed as a cold classical. It has not undergone collisions. The collisional rate in the Kuiper belt is too small. So how do you reconcile the conclusions that you drew then for 6.7p with those that we got from Arakawa?
So it's very difficult to say. So you mean that our course is planetesimals, first generation planetesimals, and there is no heavy collision, you think? So, but our results show that Cheremenko may have a heavy collision. So relationship between the Kuiper belt icy bodies and the comet is now not so. I have no idea. I'm sorry, but so let's study continue.
Thank you.
Okay, over there.
Hi, Mordecai Maclow, American Museum of Natural History, over here. So, hi. I would caution that it's not at all clear that the streaming instability can't make many small bodies. Certainly in Johansson et al. 2015, we found a rising power law down to our numerical resolution, and we were making, 10-kilometer sized objects, and I have no particular reason to think that 2 kilometers isn't possible. So forming, and of course, the gravitational collapse of a small dust clouds does form binary type objects very readily. So from that perspective, arguing that 67p could be primordial remains, I think, viable.
Sorry, so I cannot catch your explanation, but you mean that the Cheremenko-Gerasimenko keeps the original state of fluffy materials initial coagulation condition?
I'm saying that it can't be ruled out as having formed from streaming instability just because it's small. Small bodies can also form from SI.
Yeah, thank you very much.
You're welcome.
Yeah, I understand.
Hello, my name is Elizabeth Unerman from the Center for Astrophysics, Harvard and Smithsonian. And I was wondering if we could possibly learn more about the CO2 snowline and how it may have evolved in the protosolar disk in terms of location in the disk based on the Ryugu samples.
So from the Ryugu samples, so sample analysis showed that CO2 line inside. So this is a result of Ryugu sample analysis. So they find liquid water including CO2. So that means the CO2 including ice was trapped by the parent body. After that, it may have some evolution, and the Ryugu was formed. So the region where the Ryugu was formed should be beyond the CO2 snow line. If not, there is no such a CO2 ice is not included in the apparent body. So that's the reason. That's the reason.
Thank you.
Back there.
Hi, I'm Shoji Mori, Tohoku University, Japan, and I'm interested in the how the representative the return sample is of the main bulk composition of Ryugu. So I imagine that is a bit difficult question, but could you share your your thoughts?
Yes, I'm sorry, I cannot hear the final question.
Okay, I'm asking about how representative of the return sample is compared to the bulk composition of the Ryugu.
Bulk composition, so just so sample was analyzed by the analysis team. So they assumed that this material, this return sample, the size of a centimeter to a millimeter size, is a representative of bulk Ryugu, they assumed. But they analyzed so tens of particles, so they analyzed and they averaged the element abundances.
Okay, thank you.
It makes sense?
Yeah.
Martijn Wilhelm, Leiden University. So I have a question about the classification of asteroid shapes, where contact binaries were its own class. But I was curious if the distribution of the other shapes of the different components of a contact binary can tell us anything, if that maybe differs from the distribution of shapes of single asteroids.
So, you mean that, so, sorry, please explain one more.
Okay.
What is your question?
So I'm just curious what the distribution of asteroid shapes would be if you're just looking at the single individual components of contact binaries.
Mm-hmm.
And if there's any difference with the shapes of single asteroids, and if that can tell us anything.
So, what do you mean?
So, binary シングルなのかバイナリなのかバイナリの可能性なのかみたいなこと聞いてみる。
You mean that, so for example, the asteroid Itokawa is really is binary, but after that touched each other to make one asteroid. So you mean that, so the Itokawa is a previously binary asteroid. After that, it goes to a single, that kind of asteroid.
I mean, for example, if contact binaries, for example, may preferentially consist of two top-shaped asteroids, or something in that direction.
No, that's right. So, I'm sorry, but please talk after the session. I'm sorry, I cannot catch, actually.
Thank you, sorry.
I'm sorry.
Okay, yeah, over there.
Michel Bannister, University of Canterbury. These inclusions with the CO-rich material is, that's really lovely to see. This argument that Ryugu forms in the outer part of the disk, how much volatile loss would you anticipate as a result of the migration processes to get it to its current location? Because if Ryugu is, of course, a typical asteroid, then you'd be seeing that volatile loss across a large part of the population.
Yeah, I'm not so familiar with these issues, so I will answer on the mattermost. I'm sorry.
Okay, could I just to comment to the impact side of that? you're delaying the impact timing for the rubble pile formation to quite late in the process. Do you think that's consistent with the migration part of it?
So it's maybe difficult to say, so I have no idea just now. Sorry.
Okay, so any other question? Over there.
There were the three people.
Oh, okay. Oh, sorry. Oh, sorry, I missed. Okay, yeah, over there.
So hi, Arakawa-san. So I'm Arakawa from Jamstick, Japan. So I have a naive question on the catastrophic disruption origin of comets. So the comets contain anhydrous minerals and also amorphous ice. So do you have any comments on the thermal evolution of comets from the point of view of catastrophic disruption origin?
Oh, in the
So
case.
maybe small comets might be preferred from the point of view of retain of amorphous one or anhydrous one, I guess. But maybe you have comments.
So, yeah, so there is a simulation conducted by Patrick Michel. They say that so high temperature just occur around the impact area. So most of the materials are pristine material. And so these pristine materials attracted each other to make a rubber body. So that means such as if the comet nuclei is such a created rubber body, so the pristine material is kept. So, so just a simulation.
So, but the radiogenic activity may also cause the heating.
But in the case of small bodies as small as a few kilometers, the radioactive heating is not so important, I think. But this is, you know that very well.
Oh, yeah,
I think.
Thank you so much.
Okay, so next.
Hi, Anish Baburaj, UC San Diego, United States. I was curious if the composition of the asteroid could have an impact on the shape evolution.
Composition was what?
Of the composition of the body could have an impact on the shape evolution, make certain shapes more likely than others.
Composition of I think the composition of rocky and icy materials, the difference is important to affect the impact phenomena, because so difference of material strength is so different. Rocky material and the icy material it affect, and also some thermal property is also different. So I think the material property is important to affect the impact phenomena and reaccumulation of such a rubber body.
Thank you.
That's it.
Okay, so no other people? Okay, all right. Oh, no other question, comment? Okay, if so, please thank the speaker again.